let us get into some basics of, and the science which we are trying to understand. So if you look at remote sensing system or science of remote sensing, you have sun, which is illuminating all the earth surface features on the ground. And when it is illuminating it, there are four processes which take place. When I'm speaking so many words, so many sentences and all, some of you might be thinking, okay, we have been taught this is of no use to us, we already know it. So you are transmitting it. Few of you might be jotting down, noting it. So that is called absorption. And some of you, what you are absorbing right now will be emitting at the later stages in terms of your questions and all. So that is emission. And a good part of that should be reflected back. And probably because of this online mechanism, you are not able to reflect back. But I expect these bright students are interested to reflect back. And this reflection is very important. So that is what is stored by the cameras which are mounted on these satellites, and through earth stations they come on to the users. And the beauty is, data set which is collected for this blue planet by the same set of satellites with similar kind of features could be used for multi-purposes. Soil scientists, forester, agriculture scientists, geologists, geomorphologists, urban planner, you name it, and people should be able to use it. This is one of a typical diagram which you must have seen here and there. This is called as spectral response pattern, or in much more standard way, we call it spectral signature. The bouncing back which is taking place, that is represented here along the wavelength. If you see it, 0.4, 0.8, 1.2, these are the wavelengths in micrometer. 0.4 to 0.7 is the wavelength which we all are able to see. This is a visible spectra. 0.7 onwards are the wavelengths which we are not able to sense with our naked eyes. There could be some of the organisms, some of the animals which are able to see this. Now, if you concentrate between 0.4 to 0.7, you get a unique reflectance. This is great, that is the reason we are able to see and we are able to differentiate among the things. But if you further concentrate on this, you will see that this entire reflectance pattern is summing up to 20%. Or in the sense, these all responses are so much, interlocked. And to decipher among the features, you can do, but it is relatively tedious exercise. You are able to differentiate among the things, but it is not very convenient to differentiate here. This you all should understand, Using visible spectra, you can see most of the things which are there, but when it comes to differentiating among the things, then it is slightly tedious. But the moment you go 0.7 onwards, again, you have unique responses. But apart from being unique, they are distinct apart. It means you should be able to differentiate among these things very conveniently. This is the success story of remote sensing or remote sensing in non-visible spectra. You are able to get distinct responses as within visible spectra, but you are able to discriminate them very conveniently over here. And that is what helps me to understand things in a much better way. So you gather information in different wavelengths. You have something called as slits. If you remember your physics experiments, which you have done in 11th and 12th, so there in certain ways in optics, you get to know about these slits. So you can collect information in blue wavelength, green wavelength, red wavelength, near infra, you name it, and you should be able to do it. So this is a broad range, 0.5 to 0.6, 0.6 to 0.7. You can further refine them based on the response pattern. Now, when you have collected this information, it is giving you 100% reflectance, 0% reflectance, or reflectance in between. So you have something called as gray levels. It's not black and white. These are gray levels, different shades of gray. Now you have visual units like your laptop, your mobile, your iPad, your palm top, your TV, your CCTV, LCD, whatnot. So those all work on the principles. There is something called as color guns, image planes. In much simpler, we call it picture tube. So you have RGB. If you put R on R, G on G, B on B, you get something true color. If you use NIR, so you drop something and you get something called as false color. So just for the students, it should be much more convenient to understand here. This is data collected in red band, this is in green band, this is in blue band. So these are the wavelengths in which reflectance is collected. So I call it data collected. These are my image planes, RGB. I put red on red, green on green, blue on blue. I get something called as true color composite. What I can do, I want to use an IR. The reason is very simple, because I am able to discriminate among the features in the wavelength beyond 0.7. So that is NIR. So when I put NIR on red, red on green, green on blue, I have to drop one. So I have dropped the blue one. So I get something called as false color composite. So this is my true color, this is my false color. If you see this, this is a lawn. Here you have baseball kind of stuff, some gymnast kind of stuff. These are all trees, these all are settlements and all. You get to see, wow, this is looking very good. But the moment I see in false color, everything appears as red, because near infrared is being displayed in red image plane, and that reflects very high for vegetation. But if you look at this lawn, you have this baseball, you have this gymnast, but you have these openings, which were somewhat visible in true color, but which are very evident in false color. This is beauty of false color or information collected in near infrared. There are certain things which you should be able to see, but differentiating them is very challenging. But when you look at false color, you are able to see them and you should be able to differentiate even. In addition to this, if you see these all three areas, they are appearing in probably around 2 shades of green. But the moment I see in false color composite, I see at least 4 or 5 shades of red. It means same thing is becoming much more informative. That is what, entire success of remote sensing lies in wavelengths which are beyond the visible spectra. If you collect data in that, you might get to see much more additional information, which is relatively very unlikely in true color composite. And this what people try to explore and exploit and give you something more meaningful information. So this is what images are: true color composite and false color composite. These are the wavelengths in which data is collected. But when data is being looked from space, it is able to resolve between the features. There are some people who are able to see letters from far distance. Some other set of people, they are not able to see. Then what we say, their power, the power of lenses weaker. They need additional lenses, glasses like this. So that power is called resolving power. It is 1 upon focal length diopter when we talk in terms of optics and all. Herein, in lenses, we are talking about this resolving power. So this is the spatial distance which could be resolved by the sensor. So you can see an area which is appearing very gloomy, but if you see with relatively higher spatial resolution, you see greater degree of details, further same area with higher degree of details and further. So you have somewhere, 5 meter, say somewhere 50 meter cell size, 25 meter cell size, 5 meter cell size, and as close to 1 meter cell size. So here you are able to see trees, canopies even. Here you are able to get some kind of pattern, which is granular pattern, which can tell me yes, trees are there. Here you are not getting that, but you are getting coverage. So it all depends, if you are a global scientist, you want to see entire globe in one go. For you, it doesn't matter whether there is a lawn, whether there is what kind of trees are not. But if you are very local scientist, you want to see health of each and every tree. Oh, this tree got a borer, or this is getting affected because of some insect, that kind of thing. But if you are in between, you need information somewhere as a trade-off. The best spatial resolution to my understanding is 25 centimeters, Cartosat 3, which is at the behest of Indian satellites. And then you have WorldView 3, which is having somewhere 30 centimeters. So that kind of best spatial resolutions are available. And best spatial resolution means you should be able to see each and every tree, each and every entity which is standing there on the ground. That is, you are able to appreciate. So that is, with higher resolution, you can see such kind of stuff. So you get wide range of spatial resolutions depending on what is your purpose. These all are, as I said, context is God. Why do you need data? For what purpose? That is something very important, and many a times your spatial resolution defines that, depending on what you want to achieve. This is another very interesting thing. If you see this data, this is of December 2003. Same area, January 2004. Same area, February 2004. Same area, March 2004. Again, December 2004, all red, blood red is vegetation or dense vegetation, trees, those kind of things. These bright colors, these are bright pinkish colors, these are agriculture areas. Blue, black blue colors are water bodies. Cyan color is open area, and in certain cases, settlements. This greenish color is more of a grassy, wherein lignin is there, but chlorophyll is not there. As a forester, you understand this. Lignin is there, but chlorophyll is not there. So within blue-black, you get to see different shades. Dark blue-black, it means it is very deep water. Lighter shades of blue-black, it means shallowness is there or turbidity is there. Same way, redness, dark, very bright blood red, very dense canopy, open canopy, and much open canopy, and much degraded. Pinkish, these all are agriculture fields. But as I move along with months, you see that your redness is decreasing. People might say, oh, entire forest has removed. Probably not. This is a deciduous area. So your trees, they have shed their leaves. And then you are not getting any pattern of chlorophyll over there. So it is appearing like this. Same thing, if somebody clears the forest, clear felling, then also you should get to see similar patterns. But if you move to next season, new leaves are sprouting out. So that kind of thing could be looked at. Same could be in terms of water bodies. If you concentrate on water bodies, those are shrinking. At the fringes, people are growing crops. So you are getting a different cropping pattern. So some water bodies are becoming much darker, some are becoming much lighter. So we try to see these all variations, over the space and over the time. And this variation helps me to understand what exactly is happening on the ground. So people try to use data set for more than one season, and specifically for Indian conditions, wherein you do have evergreens evergreen, but lot of the area is deciduous, moist deciduous or dry deciduous. So in such conditions, you need such type of data sets.